Okay, thank you very much. Thank you to the organizers to give me the opportunity to speak in this wonderful place. So today I will we'll talk about this spin chain density matrix and qKZ equation. It's a project in collaboration with Professor Holger from Hanover. But before starting, I would like to remark something. So this is the title for basically the first part of my talk. So when we started to work with this qKZ structure, we were working in the framework of quantum separation of variable methods, and we noticed some qKZ-like structure emerging in that framework. We found something very basic, but we couldn't really understand what to do with it. So we decided basically to teach ourselves something about qKZ equation by looking to this particular problem that I'm going to talk about. So let me start by just recalling to the one or not acquainted to the qKZ equation. Where does it come from? What it is? So the first definition of qKZ equation came in a paper by Frankel and Reshetiki in '92, and they were working with this quantum affine algebras, and they basically Q-deformed the KZ equation for conformal field theory. So this qKZ equation is satisfied. Quantum homological equation is satisfied by this what they call quantum correlation function, which are basically matrix entries of product of intertwiners of these algebras they're working with, and these are highest weight state and lower weight state, so it's defined like this. And the quantum kinetic homological equation is at least in some with this notation we can define it in this way. So we have the first chain of our matrices, some operator depending on the algebra we're working with, and a second chain of our matrices. Yeah, not super familiar with this stuff, but it should be like the highest weight vector, and this the lowest weight vector. Yes. And that's it. So let me just recall a brief overview about people working on the qKZ equation. For sure, it's not a complete list, so it's more what I went through when I was reading about stuff. So one must mention that there was a definition of qKZ equation that predated the paper by Frankel and Reshetiki. It was a paper by Smirnov, where was working with some form factors in a particular point of complete integrable models, and they satisfied the qKZ system. Later, Cherednik also worked in this field and built some generalization of the qKZ equation in terms of R matrices associated to generic affine root systems, and which led also Felder later to introduce some these other people to introduce what is called like boundary qKZ equations. And for example, there is I think useful paper by Vlar, quite recent, and he talks about this boundary qKZ equation. Later, Felder also worked with the qKZ-B equation, so basically he was dealing with this dynamical algebras or related to phase models. And other people, basically this list of people here, they produced quite vast literature about the qKZ equation, and I didn't remember all the papers because it's kind of big list, but it's kind of important their contribution. And more recently, in a paper by Di Francesco and Saint-Justin, and more recently by Finch, Weston, and Saint-Justin, they showed how this solution to qKZ and qKZ-B equation are basically ground states for some integrable model in a particular point, so in the combinatorial point, basically, and that's it. And last, I would like to recall this paper by Aufgebauer and Klumper of 2012. And this is particularly important for me because if you know this paper here, in my presentation I will just basically recalculate the results. So it's basically the same results in a different case. So basically they showed how certain density metrics in homogeneous density metrics satisfy the qKZ equation working with this quantum transfer matrix framework, so of infinity lattice. I will basically do the same, but for finite chain. So maybe if you already know this paper, it's not much surprising what I'm going to show. Okay, so just to give a table of contents of my talk. I will just define the model that I'm going to work with, define the density metric, so the main object of my talk, and then I will show how it is a solution of the qKZ equation, and then I will focus, as it was done in the paper, on the two-side density matrix and see how to characterize it in particular. In the second part of the talk, as I said, time, I think so, I will explain what I mean with this qKZ-like structure that emerged in the separation of variable framework. So I will just give some introduction on the SOV method, and then I will explicitly show what I mean with this, and then we can take our conclusion. Okay, so let's start by defining the model. I take just the plain Heisenberg, periodic Heisenberg spin 1/2 chain. Very well. So as usual, the Hilbert space is a tensor product of n copies of c squared for a total dimension 2 power n, and the Hamiltonian can be written like this. So here I just wrote the generic Hamiltonian. If we take all the coupling constant equal, we get the XXX model, which the one we are going to use. And as usual, the operators appear in here, just polymatrices defined non-trivially just on some tensor product. Good. We want to study this model here in the algebraic representation of the model, as usual, like the algebra Bethe-Ansatz. So what we need for that, we have to define our R matrix. So I will take my rational R matrix in this form, which is a rational solution to the Young-Baxter equation, but I guess everybody knows. And I would like just to list few of the properties of this R matrix, since all the proof of the statement listed after, they're just proven by using these very few properties. So the permutation point, if you take it in 0, we get basically permutation operator. Antisymmetrizer, we get the singlet projector. Sorry? Yeah. And then we have the two unitarities, so unitarity and crossing unitarity, which have this particular form. Yes, here's just the definition of the action of the permutation and the definition of the singlet projector. Very well. Once we introduced our R matrix, we, as usual, introduce our monodromy matrix. So it's a chain of R matrices evaluated in the spectral parameter lambda, and each side contains an inhomogeneity. So we are defining an homogeneous monodromy matrix as usual, and which is defined to act on this space here. So the monodromy matrix, as we know, contains all the generators of our associative algebra, and the commutation relation of this associative algebra, they come from the RTT relation, which are consequence of the Young-Baxter equation. As usual, everything we know very well. So, and for example, the Casimir of the algebra is this quantum determinant, which is generated in this way. As usual, once we define the algebra, we want to see what's the connection with our quantum model, so we have to define our transfer matrix. And of course, we know very well that it commutes for different value, there's a typo, values of the spectral parameter. And finally, one can define the trace identity, that in this case, it looks just like this, so one has to take the homogeneous limit of this derivative, and one finally finds the Hamiltonian. So the idea in the algebraic Bethe-Ansatz framework is to solve the eigenproblem related to this transfer matrix, and in contemporary, solve the eigenproblem related to our H, to our Hamiltonian. What people do normally when dealing with finite chain is use this algebraic Bethe-Ansatz, determinant formula for scalar products, and then maybe computational form factors and correlation function. And this is also possible. It's very, let's say, nice and easy to do if we define some inverse problem that it was done in the past. And since the definition of our inhomogeneous density matrix, it's highly based on the let's say, how this inverse problem looks like, let me just remind what the inverse problem is. So the main point of the inverse problem is to express some local operators on the quantum space in terms of this associative algebra of the representation. So some let's take some elementary operators or some matrix with just one non-zero entry in them, and thanks to this Kitanian, Maillet, Terras, they give us this nice formula in order to represent some quantum local operators in terms of elements of the algebra. So, given this form of the inverse problem, it's kind of natural to define what I'm going to define. So, this density matrix. So, imagine to take this, take some sandwich with the ground state of the transfer matrix, and let's imagine to remove these, and so let's take the matrix with all the form factors as entries, and we basically get to this. So we would get to this with just one entries, and then it's simple to generalize to many local operators in this way. To get the form factors, one should also substitute all the lambdas to inhomogeneities, of course. But let's just... Sorry? Yes, you're right. Sorry. Yes. Okay. So we will work with this object and show when it is actually a solution of a well-suited, well-written qKZ equation. Here the taus are the eigenvalue of the transfer matrix relative to these ground states that I right and left. M? M is the monodromy matrix. I called it T before? No, it's M. Yeah. M for monodromy. yeah, it's right. Yeah. I mixed literature. Yeah. So, few comments. I'm keeping the number of quantum space even. Why? Because I would like to have these ground states to be singlets, basically. So it's important to be like this. So these phi L and phi R are the left and right eigenvectors, and as I said, this function tau are the eigenvalues relative to these ground states. And again, these are SU2 singlets, and my density matrix is by construction an SU2 invariant object. Okay, so let's arrive to the main point. I said that this density matrix will satisfy some sort of qKZ equation. So before showing that, we have to define the qKZ equation it satisfies. So it is, yes, we already saw this probably in the lecture by Professor Klumper. So we have this operator acting on this endomorphism space between these two spaces. And we have some normalization constant, the trace over the nth auxiliary space, a first chain of our matrices, and the other chain of our matrices, which is basically the inverse of the first chain. These are the ground state of the transfer matrix. Different? Well, it's the right ground state and the left ground state. The one you build with a chain of B or C, let's say. Yeah, the eigenvalue is the same. I mean, yeah. But we'll see later that just for the qKZ equation, we could release the constraint that these are ground states. But I will make this remark again later. So, yeah. And in the center here, we have the singlet projector on these two auxiliary space M bar and the new space M star that I'm adding in the definition of this operator. Then here we will put our density matrix and here just some identity. And at the end of the day, I will reproject this M star space to the M bar in a way to have objects just defined on the same spaces. Yes, this normalization constant is given by this. It's basically given by the fact that when I annihilate this R matrix on this, we produce one term from here. So it's just that. Yes. yeah, it's just plain spin-off XXX, nothing more. Okay, so before giving the main statement, let me just define this object, which is just a renormalized R-check matrix. And one can prove that, well, quite easily, that the action of this R-check matrix on our density matrix has the effect of exchanging the n and n plus 1 parameter terms. And it's very easy to see. Just it's enough to apply this transformation to the operator content of our density matrix. And then finally, we have the main statement that this density matrix is a solution of the qKZ equation in the moment that one of these spectral parameters is equal to one of the inhomogeneities. There is a shift, yes. Yes. By eta, yeah. When one of the spectral parameters is equal to one of the inhomogeneities. So here I just displayed if we choose the last one to be one of the inhomogeneities, but thanks to the lemma we can just always shift to whatever place we want. Yes, I think in the paper by Klumper they show that in the thermodynamic limit this holds in general, not just in the inhomogeneities. But for finite chain this is true just when lambda m is equal to one of the inhomogeneity. Okay. I would like to give a sketch of the proof of this. So in order to prove this result, again, we just follow the line given by the paper. One has to define this dm plus 1 density matrix, where in the site m plus 1, we select the same spectral parameter lambda m shifted by eta. So it's not so difficult, we can do that. And then one can show the following. So if we take the trace over the space M of the action of AM of dm plus 1, one would get dm. And if we do the same operation, but we take the trace of the space M plus 1, we will get the action of AM over dm. So we have two identities, 1 and 2, and one can show if one of these lambdas is equal to one of the inhomogeneities, the two identities actually coincide, and so one has proved the statement. Let me do some content. So all the identities used to prove this statement are just based on the operator content of the density matrix. So I never use the fact that these are ground state or these are singlets at this point. So for this result. What does it mean? It means that in principle one could put also different states. Well, different states possibly with the same eigenvalue in order to have good normalization, but that's it. And as I used just properties of R matrices, one could use other R matrices which have the same properties, like the trigonometrical one, for example. And so one can see. So these two are very easy to prove. To prove this, it's a bit longer, but it's not difficult. It's just some manipulation of R matrices. Okay, once we got our main statement, we can start to look at particular points. So I would like to focus on the D2 density matrix. So first of all, let me remark that the trace of dm is equal to 1 because it's normalized like this. So by symmetry, we can fix the D1, so it's like just a trivial matrix like this. And by the same symmetry consideration, we said it's an S2 invariant object, we can write our D2 in this way. So like a sum of projector on the singlet and on the triplet. Then, together with the fact that the trace should be 1, at the end of the day, I can just rewrite it in this way. So we have just one omega, not two omega functions. And kind of, we already saw this in the presentation on Monday, right? Yeah. And we can just use some unity metrics and the singlet projector. This is very nice. So at this point, the analysis of the D2 passed to the analysis of omega, since it's the only non-trivial object. So let me remark that this is true for whatever size of the chain in form. So the form will be always the same. What will change, of course, will be the omega function, which contains all the inhomogeneity and all the information about the mode. So let's try to analyze this, this omega function. The first thing to do, of course, is to plug this form in the qKZ equation and see what we get, what kind of functional equation we get on omega, and we get just this, which is basically the same equation they got in the quantum transfer matrix formalism. And few other properties, so it's symmetric for exchange, and if I multiply by the eigenvalue, lambda 1, lambda 2, I get some polynomial, because by construction I have just a chain of monodromy matrices, and of course it will be a polynomial. Yes, at this point it would be nice to give a solution to this, but so what I did was I start with a small chain and try to see if it's possible to find a solution, but we have enough points to build an interpolation formula for the solution just for basically n equal 2 more. We need more information that we don't have here. Okay, so the last point we could do is to try to characterize a bit more this omega function, and we try to reproduce this trick that was used in the paper, so to join this omega function to a modified transfer matrix and see what's the connection. In the end of the day, I don't know how much is useful for us, since we are keeping things finite, but still, this trick works also for finite chains, so this is the result. So what we have to do is to define a new transfer matrix, so it's basically the usual transfer matrix where we add two quantum sites, and we evaluate this transfer matrix in this particular combination of points. And for epsilon going to 0 here, these two matrices, they belong to these fusion points, right? What does it mean, fusion point? For us, it means in particular that the ground state of this transfer matrix for epsilon going to 0 will factorize exactly in the singlet on these new two quantum sites time the ground state of the old transfer matrix of the usual one. And this is very important to prove the following. So first of all, we just choose a proper normalization between the two eigenstates, left and right, in a way that is equal to 1. And then we can show this. So if we take the logarithm derivative of the eigenvalue of the modified problem, and then we put epsilon equal to 0, well, the first identity is obvious, it's just the same. And at this point, we'll inject some new modified monodromy matrix, well, transfer matrix, since I'm taking the trace over the auxiliary spaces, and I have to modify, this is a 2. Yeah. And by doing some manipulation with the explicit form of these monodromy matrices, one can get at the end to this expression. So in principle, this expression is not simpler than this. Of course, we don't know this action on the states of the monodromy matrices. But injecting this monodromy matrix, we are able to reproduce the D2 density matrix, basically. And we know in form how it looks like. So at this point, this expression is very easy to compute because it's just a trace on 1, 2, 4 spaces. And we know very well the form of everything. So if we compute that, what we get is this, that the logarithmic derivative of this tau tilde of lambda for epsilon equal to 0, it equals to this, where here it appears this omega function that was interior to omega. So it's a way to link our omega function to this modified problem. Then if one went to thermodynamics, could link this omega function to the kernel of the algebraic, of the Bethe-Ansatz formally, yes, technology for thermodynamic limit, and it was done in the case of quantum transfer matrix. But for us, since we want to keep stuff finite, it's kind of the end of the story at the moment. I don't know how to use more of these. Okay, so maybe I was a bit too quick, but anyway, this was basically the first part of the talk. So I showed how this density matrix is still a solution for this, written like this qKZ equation, even for finite chain. Very well. But okay, now I would like to give you an idea of what we were looking at the beginning. But one must be honest. So the two parts are basically disconnected at the moment. this was sort of exercise we gave us in order to understand a bit more qKZ equation, but it's not necessarily related to the SOV method, etc. So anyway, let's go through the second part. So little introduction about the separation of variable method. Was a method introduced by Sklein in the 80s, and the core idea of the method is the reduction of multidimensional problem with series of one-dimensional ones, like separation of variables also in classical mechanics is. And it was maybe led by the possibility to give deeper insight on quantum integrability. I don't know if it did, but at least it gave the opportunity to study and analyze models that were not possible to be studied with the algebraic Bethe-Ansatz, for example. So like spin chains with particular boundary conditions, like anti-periodic, non-diagonal, or even open spin chains, right? Open spin chains with boundary conditions were not possible to be studied with the algebraic Bethe-Ansatz. So again, a short bibliography where people that using this method. Of course, we have the first original works by Sklein on the Gurechev-Chaplin-Top, Godel model, and the Yanjan SL2. Then other people worked on Sine-Gordon, on Tau2 model, SL2 spin chain, Sine-Gordon model, and all these other. And in particular, let's say my contribution came in the context of open spin chains, so it was possible to analyze open qKZ and xYZ chains with the most generic boundary conditions, so without imposing any constraint on the boundary parameters. Okay, let's see how it works. Basically, so let's take again, for example, an Heisenberg chain, but this time not periodic. So we will insert some boundary matrix here. Again, the monodromy matrix, which I call T now. Sorry. It's defined like this, and the main point is to rewrite our B operator as a polynomial in this way, and because of the RTT relation, this time is proper RTT. Yeah. We know that all the polynomial coefficient of B, they commute among each other, so we can just diagonalize them simultaneously. And the main point is basically to rewrite our B operator in this way, where the X hat are the operator zeros of our B operators. Sorry? Here? Yeah, it's just the coefficient of the first. Yeah, because I defined B hat like this. Yeah, it's a number, sure. Yeah. But thanks. Okay, it's very important to be K12 different from 0, because if not, B wouldn't be of maximal degree, but and so it would be nilpotent, and we can't basically diagonalize it. So it's important to be like this. Okay, these are called the separated variables, and written like this might seem a bit obscure how to get them, but once you try to build the explicit representation, it's kind of clear what they are and how to characterize them. Then we can look at the other generators of the algebra, how they behave in these optics, let's say. So we want to diagonalize B. What happens to A and D, for example? Well, we can define these operators, which are basically A and D evaluated in the eigenvalue of the operator roots of B, and they become these X minus and X plus, which they are called like this because they behave like ladder operators on this particular basis, which will be our SOV basis. This is due to a theorem by Sklein that proved these, exactly for this model, it proved these. So the commutation of operators of these two operators gives a shift in eta. Okay. What is this state? This is a state characterized by the eigenvalue of these operator roots. So at the end of the day will be just the eigenstate of B. And so our A and D operators acting on these will shift the index the eigenvalue of B of this plus or minus eta. And here it's the very core of the analogy with my qKZ-like structure, but it more explicitly later. So just to conclude the part on the generalities on the SOV, what can do now normally, it's of course to characterize the spectrum of the transfer matrix using this SOV basis that one can build in this framework. So one has to identify the proper B operator and the operator zeros, and finally the transfer matrix, which will be as usual the sum of A and D of this model, and can plug this form in a sandwich between an eigenstate of the transfer matrix and one of this SOV state. One would get expression of this type, which finally boils down to this Baxter-like equation. So it's not Baxter equation because these hold true just for the operator zeros. They are not general for lambda. But it's a full set of Baxter equations. So xn with little n going from 1 to the size of the chain, basically. So we'll see how these operator zero are related to the inhomogeneities. So they are basically the inhomogeneities, okay? And one can prove this, and this is basically the characterization of the spectrum in this SOV framework. But, okay, for us it's not really important this, because we want to take a step back and see this qKZ structure arising. So what we want to do now is to build explicitly this SOV basis for an explicit system. So we take our Heisenberg chain with certain k metrics in a way that B is not nilpotent, and to start to build our basis, we use a reference state. So, for example, you can take the all spin down reference state, and one can show that this state is an eigenvector of B, of this B operator, with this eigenvalue here, given here. And then how to build all the other states in the basis, but we use our Sklenin theorem. We know that the A and D operators are ladder operators when evaluated in these operator zeros, and so in this, yes? Yes. For dealing with open, well, this is not open chain, but anyway, for the open chain, yes, it exists, but they always have to put some constraint on the boundary parameters at a certain point. With this method, you can just leave them free. No. Yes. In the yes, the last yes. Well, again, you get the characterization as I showed before. It's not maybe explicit, but it's yes. Yes, yes. Is that the point? When you impose constraints, is to have a reference state. In general, you don't. Yeah, it's the main point. For example, just let me mention the same stuff you can do it with XYZ, where you don't have a reference state from the beginning. But in this case, it's no problem. You get the same result as for XXZ. It's more general. Anyway, so we can build our SOV basis state like this. So we have our label H that can be 0 and 1, depending if this is 0 or 1. And one can prove that this is actually eigenstates of our B operator, and they look like this. This will be basically our object entering this qKZ-like structure. I want to put like because we will see why. Okay, so let me define the operators that will appear in the qKZ-like system. So we have what I call flipping operator, which is again our renormalized R-check matrix, and the cyclic operator. So what is this cyclic operator? It's basically the product of the K matrix, so the boundary matrix they put in my monodromy matrix, and rho is the cyclic permutation in the spin basis. So the action of rho circle here is given by this, basically. It's kind of simple. And once we've got this definition, we can give the first statement of this part. So the action of this R-check matrix on the SOV state will flip the two H labels, but unfortunately in a different, we get a state of a different representation. An SOV state built by representation where since the beginning I exchanged the inhomogeneities psi n and psi n plus 1. Okay? So it's not states of the same representation. If we act with this cyclic operator, with the last term, last h being equal to 1, we get a state of this type with h here getting equal to 0, but again, with a different representation where I'm permuting cyclically all the inhomogeneities in this way. So it's what I wrote here, where this epsilon is just the eigenspace of B. Okay, up to here maybe it's not so exciting because I mean I'm getting states of other representations. Yes, to prove this proposition is very easy. One can look, for example, at the action of this transformation of the monodromy matrix, and one can understand exactly what happened. But when I have this qKZ-like system and I put them together, the identities 1 and 2, one get the second proposition, which is the qKZ-like equation. So we can define a qKZ-like operator Sn given by this definition, so rho and our R-check matrix. And if I apply Sn to a SOV basis state with Hn equal to 1, I get another state with Hn equal to 0, but this time in the same representation. So this is coherent, and so it works. This is very in the core of the SOV method. I just showed how I can rephrase the fact that A and D become ladder operators, and they kind of look like these normal qKZ operators. Again, I use like. Why like? Because this is not really any qKZ operators. We have no appearance of any shift here, for example. And the shift here is a, how to say, it's on a representation level. To see an actual shift of the inhomogeneities, one should act with B and look at the eigenvalue, and then you would see the shifts. But if not, it's not so. It's sort of qKZ-like structure, but that was kind of the end of the story for us. We couldn't understand if there was some deeper meaning. Sorry? Yes. This shift, okay, the action of this Sn acting on this SOV state produces a shift of -1 in the label H, okay? But it's not an actual shift in the inhomogeneity if you look at the explicit expression of this state of the inhomogeneities N, for example. It is a shift in the eigenvalue of B relative to this and this state, basically. You can see explicitly the shift just on this representation, on the label, not on the inhomogeneity. No, it's, yes. And this proof just followed by using manipulation of, by using the qKZ-like system I showed before. So as I said, it's like system because there is no trace of shift in Sn. The map state are the same representation at least, okay? And yes, and the only shift we can see in the eigenvalues. Okay, and that's basically, yes. Yes. No, these are, okay, when I define the state, you can see explicitly what they are. Yeah. So I act with a chain of A operators. One, so I'm selecting the sites where these. Yeah. Yeah. It's the eigenbasis of B, basically. Yes. The action of this qKZ, like, yeah. Yeah. And I could also act with when h is equal to 0, but I would get something else that is not. Yes. 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 That's I don't know. For me, was curious, but again, yeah. Yeah. Mm. Yeah. Yeah. And yeah, that's basically it. So first part I showed how to deal with this result of density matrix in the finite case. And okay, again, it seemed like disconnected the two parts, but we really wanted to understand what kind of physical objects satisfy this qKZ equation that maybe could have been useful in this S of E setup. But for the moment, it's just like this. So I'm done here.